Hello, I'm Jay McClelland, and I'm going to talk to you today about this question. Are people still smarter than machines? And if so, why? In 1986, Dave Rumelhart and I asked, why are people smarter than the machines that we had back then? And the answer we gave was that people use graded signals propagated among simple processing units to solve the constraint satisfaction problems that arise in natural human tasks like perception and language processing. And they learn to solve these problems by adjusting the strengths of the connections among the units, avoiding the need to program knowledge in. And in some ways, systems based on these ideas have turned out to be pretty smart. Deep learning models build on these ideas and extend them to capture the phenomena that motivated the framework in the first place. They function well enough to be in use every day for speech recognition, many other things. They exceed human performance in games like chess and Go, getting better every day. So in some ways, humans are no longer smarter than machines. But I think it's still true that humans are smarter than machines in several important ways. Neural networks require massive data sets and show poor out-of-sample generalization. To learn to use context and language, today's language models are trained on a corpus of up to 1 trillion words. To master chess or Go, AlphaZero learns by playing up to 120 million games. Models generalize poorly if tested with examples drawn from a different distribution than their training data, and in contrast, humans are often able to learn much more quickly and generalize from much more limited experience. Several people have illustrated this in other work, but my student Andrew Nam and I have explored this in the domain of Sudoku. And we found that we took humans with no prior Sudoku experience, and we told them that the goal of the game is to start from a grid with some digits filled in and add digits, so that each house, that's a row column or 3x3 box, contains exactly one instance of each of the digits. They're shown a grid like the one at the left, and they're walked through the reasoning that allows them to determine that one of the two candidate digits that occurs 3 times in the grid must be the digit that goes in the green target cell. Many participants, who we call solvers, get the idea after a few trials with similar grids and explanatory feedback when they make errors, and after that they only make very occasional errors. So we were also interested in how well could they generalize from very limited experience. During training, they saw grids with a single target cell within a single specified house, which was either a column or row, and there were only 4 digits that ever could occur as the candidates for the possible solution digits. During the test phase, however, we allowed anything to change: which house was the target house, whether it was a row or column, which cell was the target cell, and we allowed the digit set to switch from the ones that had been used in practice to a novel set that hadn't been used before. And what we found was there was virtually no effect of switching the candidate digit sets. Reaction times and accuracies were virtually unaffected. But if we switched the house type, there was a small impact, 5% decrement that only lasted for a couple trials. So it wasn't perfectly transferable with respect to house type, but very quick adaptation from a change. And we compared these human abilities to Sudoku's problem solver, DeepMind Sudoku problem solver, asking if it generalized and learned as humans do. For one thing, it learned much more slowly. It did generalize perfectly across all the positional variables because the ability to do so was built in, but it didn't generalize perfectly across the digits because the designers didn't build that in. Instead, they trained it with a very balanced training set in that regard. We were able to build that same ability in ourselves using a similar trick to the way they built in the generalization across position variables. And we overcame this limitation, but it still learned slowly. So should we conclude that the human ability the human advantage over most machines comes from building systematic generalization in. Fodor and Polition argued that we can only understand novel sentences because our minds are designed to process language and thoughts according to systematic generalizable rules, such as modus ponens, which is described here. And Marcus, Lake, Ullman, Tenenbaum, and Gershman have made similar arguments, proposing that systematicity may be an inherent feature of human cognition. But I'd like to present the argument against building structure in. And basically, it's the observation that neural language models that avoid and other models that avoid building structure in far outstrip models that rely on explicit systematic generalizable rules. That's why neural networks have been able to succeed in the ways that they have. Humans often fail to perform in the systematic ways we'd expect if systematicity is built in. This is another basic. Humans are very, very content sensitive in their reasoning. And furthermore, the human ability to exhibit systematic generalization is highly education dependent. We found that this was so in our Sudoku experiment, and similar observations have been made by linguists and mathematics educators. Only those with advanced educations or on their way to getting them are able to reason systematically as they do. So the interim summary I'd like to offer you is this. Fodor and others may be right that advanced cognitive abilities depend, at least in part, on the ability to reason by means of the application of systematic generalizable rules. However, this ability may be an acquired human ability rather than an inherent trait of the human mind. And instead of seeking to overcome the limitations of today's networks by building systematicity and other abilities in, it seems worthwhile to consider how these abilities might be learned. So just to generalize the question and step up a level here, I'd like to ask in the last few minutes of my talk, what will it take to build machines that are truly intelligent? Well, to answer that, we first have to decide what we think it means to be intelligent. And I've drawn inspiration from this quotation from Henri Poincaré, who said, "It's by logic that we prove, but by intuition that we discover." Einstein is said to have said something similar. The intuitive mind is a sacred gift, and the rational mind is a faithful servant. These thoughts, together with the findings I've reviewed already, suggest a more specific version of our question about how we are going to build machines that are intelligent. What will it take to build machines that can exploit intuition and acquire systematic cognitive abilities? So we can think of human experts maybe as people who have these kinds of skills. And Anders Ericsson was a psychologist who studied the acquisition of expertise. He argued that expertise requires 10 years of deliberate practice. This involves focused effort directed by expert coaches to provide direct instruction and explanation, guiding the student towards better and better skills. Emerging experts often become their own tutors and guide their own future learning. And as scientists, this is exactly what we're supposed to learn how to do. We're supposed to learn how to figure out how to create new ideas and new think for ourselves within them and teach others to do the same. Here's a task that I think exemplifies some of these things that I found in the New York Times a few months ago, and I'll share with you briefly. It's a little game similar to Sudoku called Two Not Touch, and what you're given is the instruction to place 2 X's in each row, column, and bounded region in the grid. No 2 X's can be adjacent, not even diagonally. And with that instruction, I've been able to teach myself how to play this game, and I'm sure you could too. In fact, when I've given talks about this before, I ask people to begin to solve the problem for me. And somebody immediately says, oh, we could place X's in the 2 ends of these 3x3, 3x1 regions, because there have to be 2 X's in there, and the only way they can be positioned without being adjacent is by being at the two ends. So just from the instruction, you can begin to solve on your own. I can also give you ideas. I could tell you that, well, an important thing for you to realize is that you can't always figure out where x's should go directly, but you can often figure out where they cannot go. And after having said that, I can tell you, well, gee, consider this situation here. Whenever you have a bounded region that's all in a single row or column, since the two x's in that row or column, there have to be two x's in there. There can't be two x's in any of the other cells in that row or column. So now I've given you a generalizable rule towards solving or reaching the sub-goal of ruling out location. And with this kind of information, it's almost enough to solve at least a simple puzzle like this one. So the types of learning from instruction and self-instruction that I've tried to illustrate here are the following. We're able to understand the task itself, the goal and the relevant constraints just by understanding instructions, and we're able to deploy them immediately to find steps towards solution, as we've discussed in this problem. We can understand and discover general rules that we can then exploit. And we can identify a sub-goal or have a sub-goal identified for us, and then general rules that allow us to reach that. We can reformulate the problem, like find all the places where the x's can't go. That's kind of like a reformulation of the goal in some ways. So all of these things are things that we can do from language very easily and directly employ to systematically improve our behavior. I'd like to mention one more form of learning from instruction, or actually from sometimes self-instruction among real thought leaders like Einstein. This is providing a conceptual framework in which logical and mathematical operations and relations have meaning. This may be particularly relevant for many domains of science and mathematics and may help us understand what intuition really means. And intuition may be the appreciation of a previously undiscovered relationship within an underlying conceptual framework. And we may eventually need to write equations to express these relationships, but what's important is the relationship itself, and that's the insight and the intuition. Just to illustrate this briefly, I'm going to consider this example from trigonometry. Many students are confused. How could it be that the cosine of minus theta is equal to the cosine of theta if the cosine of minus theta is equal to minus the cosine of theta? That's what you might think for both of them, right? Well, it makes perfectly good sense if you understand what cosine of minus theta and cosine of theta mean in terms of the unit circle. If theta is a position on the unit circle that you reach by rotating in this direction from the 0 position here, and minus theta is the position you reach by going the same distance in the opposite direction around the third circle. And if cosine is an expression for x coordinate of the position, then you can see from the diagram that the x coordinate of minus theta and the x coordinate of theta are the same. And similarly for sine, that their coordinates are the same distance, but in the opposite direction. And that's what these two expressions mean. So I'd like to point towards the next steps that I think we should be taking to achieve human-like cognitive abilities in neural networks. Most deep learning models rely on mapping inputs to outputs or predicting future inputs from past inputs or learning to maximize reward. We need to add to this by teaching them to engage in discourse as people do, including them teaching them to do these things, to follow instructions, to adopt specified goals and sub-goals, to conform to specified constraints on allowable actions, to make targeted corrections to their behavior, to understand and importantly, to provide explanations, and to connect language and symbolic expressions to an underlying conceptual framework. Ultimately, of course, we need to teach them how to discover how to teach themselves all of these things. So these are the questions that we're working on now in my lab, and I'd be excited to engage with anyone interested in pursuing these directions. Thank you for your attention.